Gratitude for the organizers for organizing this nice workshop and for inviting me to come here to Montreal. I'm really enjoying everything of this conference so far. And today I want to tell you about entanglement and in particular its dynamics. So I talk about out of equilibrium systems and how entanglement evolves with time. But I'm considering not unitary dynamics, I'm considering systems in which there is some source of dissipation. Now, let me start with this is the outline of the talk. And as I anticipated, so the goal is to try to understand how entanglement and quantum information spreads in systems. So here I'll talk about integrable systems in the presence of dissipation. Now, this is a very, very hard problem because entanglement is a very difficult thing to quantify. And moreover, I'm discussing quantum many-body systems, okay? So I have an extensive number of degrees of freedom. These are strongly interacting with each other. So in principle, this problem is very, very hard. Now, this talk is divided into two parts. So in one part, I will discuss the case in which you have dissipation, which acts all over the system. So I have a one-dimensional model, and at each side of the model, there is some dissipative evolution. And to encode dissipation, I will essentially use the Limblad framework. Okay, it is one way to incorporate dissipation in quantum systems. And then in this talk, I will focus only on free-fermion and free-boson models. And essentially, the reason is that generic quantum many-body systems are hard. So the only thing that we have been able so far to tackle are free systems, essentially. And I hope this is enough entertainment for you. Let's see. So the main message of this talk is that it's possible, at least for integrable free systems, to incorporate the effects of dissipation in a kind of hydrodynamic framework, okay, which gives access to a simple description of entanglement spread, okay. And this, I mean, in the literature, it goes under many names. So one name which is quite popular is quasiparticle picture, okay? And the reason why there is this name is that because entanglement is propagated by free-like excitation. The punchline is that if you have a generic quadratic systems, meaning that you have a fermionic or bosonic quadratic Hamiltonian with generic linear dissipators, essentially you can employ this hydrodynamic picture. In a second part of the talk, I will somehow consider a different setup in which the dissipation acts only at a site, okay? So it's local. And it can be treated essentially as a dissipative impurity. And what I want to show is that these dissipative impurities actually can enhance the entanglement of your quantum many-body system. And then at the very end, if I have time, I'm not sure I'll get there. So I will discuss some different setup, named the setup of quantum trajectories, and I will compare the findings that, in this setup with those of the Limblad equation. Now, as I said, so I want to talk about entanglement. So to have you on board, let me make some few preliminary remarks. So it's very hard in general to quantify entanglement, except, I mean, when you have pure states. So if you have a state which is globally pure, so a system which is described by a globally pure state, then there are several quantities that you can employ, so namely von Neumann entropy or Rényi entropies. However, as I anticipated, as you know now, so I'm going to discuss dissipative systems, so Limblad equations, and in that case, the system generically is not globally in a pure state. And then all our building falls apart because these quantities here are not anymore good measures of entanglement. So the dissipation introduces some spurious correlations, which are not easy to distinguish from the genuine entanglement content of the system. Fortunately, there are some quantities that you can use. So for a state which is globally mixed, you can employ the so-called logarithmic negativity, which has been introduced in this paper in 2002. And this quantity is defined in a very weird way. So it's defined in terms of this partially transposed reduced density matrix. So this is defined as follows. So you have the density matrix for A plus A bar here. And then this is written in a basis for A and for the A bar. And then what you do, essentially, you transpose with respect to the degrees of freedom of the A bar part. Okay, so here you see these two indices L and J are switched. This object is not positive definite anymore, unlike the density matrix, which is always positive definite. And then the negative eigenvalues, essentially, you can show they have information about entanglement. So this quantity actually is very difficult to compute, even for free fermions. So it can be computed with the Gaussian techniques for free bosons, but for free fermions, this is not the case. Now, before starting, so let us summarize what we know for the case in which there is no dissipation in the system. So in this case, so what you have in mind the quantum many-body system. You start from a state which is not an eigenstate, so you drive the system out of equilibrium. And then what happens is that generically there is a robust entanglement production, namely that if you look at the von Neumann entropy or any entropies, they grow linearly with time. Okay, and this is one nice piece of physics that we learned in the last 10, 20 years. Now, for integrable systems, this phenomenology can be understood in terms of a simple hydrodynamic picture. Okay, and the core of this picture are the so-called quasiparticles. Okay, emergent quasiparticles. So what happens is that you have your initial state, and then all over the place, what happens is that pairs of entangled quasiparticles are produced. So these quasiparticles indeed are entangled, and then as they propagate, they spread this entanglement. Okay, and then you see that essentially at short times, what happens is that the number of quasiparticles that are shared between your subsystem and the rest, which give the entanglement between these two subsystems, essentially is given by the width of this light cone here. So this width grows linearly in time. So at short times, the entanglement entropy, let's say, grows linearly. And then at very long times, what happens is that it saturates. This picture, so far, so this picture was derived in CFT, in the context of CFT, and this is one of my few links with the conformal field theory. But at the beginning, it was thought as just as a cartoon picture of what happens in reality. So I mean, since then there have been some developments. And actually, what here I'm trying to summarize what we know now is that actually this picture can be made quantitatively accurate. Okay, so in integrable systems. So this started with the free fermions in this paper, and then we conjectured a formula that holds for generic interacting integrable systems. And the formula is this one here. So you see this formula has two terms. So there is a term which is linear in time. And then this term acts at short times. And then at long times, this term doesn't contribute. And then what happens is that the entropy becomes proportional to the subsystem size. So L here is the subsystem, the size of subsystem A. And this gives the volume law for the entanglement entropy. Now, so another thing that you should observe here is that there is this integral over d lambda. And now if this integral is confusing you, you can think of the free fermion free boson case. And essentially, this lambda variable is just the quasi-momentum. So this integral is essentially the sum over the quasi-particle that are present in the system. Now, something that I would like to stress about this formula is that there is some kind of universality. And this universality comes from thermodynamics. So essentially, in this formula, what answers are two ingredients. So there is this S, which is the some entropy. And this actually is the entropy density, sorry, it's the density of thermodynamic entropy of the generalized Gibbs ensemble that describes the steady state that arises at infinite time. It's a quantity that knows only about thermodynamics, okay? And these V's are the velocities of these quasi-particles that I was telling you about, and these are the excitations that you have in your model. Now, the message here is that to describe the dynamics of entanglement, you don't need to know all the details about the quench and about the many-body system that you are dealing with. You just need these two parameters. Now, in this talk, I want to try to go beyond this, and I will try to incorporate effects of dissipation And to do that, I mean, I have to choose a way to treat dissipation, and the specific way that I will choose will be given by the framework of the Lymphatic equation. Okay. Now, the Lymphatic equation is an equation for the density matrix of the system, and you see you have the usual unitary part, and then you have all these extra terms here, which encode the dissipation. So the dynamics is not unitary here. Here there is an I, here there is no I. So, and these operators L encode the system-bath interaction. Okay. So this equation, I mean, doesn't provide, I would say, a complete description of dissipation, because I mean there are some assumptions here. There is assumption of Markovianity and so on, weak interaction. So this is a well-defined framework, but it's I would say it doesn't provide a complete description of system-bath interactions. So we have a very difficult problem that we have to solve. So we want to see what happens to a generic many-body system when you have a dissipation described by a Lymphatic equation. So you have a difficult problem. So one strategy to attack a difficult problem is to go to a trivial system, to the simplest system you can think of. So, and here the simplest system that I can think of is free fermions on a ring, free hopping Hamiltonian on a ring, which is called XX chain in the spin language. So this Hamiltonian is diagonalized by going to Fourier transform. You get this simple dispersion, and then from the dispersion you can get the group velocities of the fermions. Okay. Now, and I have a simple Hamiltonian. I add a very simple form of dissipation, and the dissipation that I choose is gain and loss dissipation, which is given by these two operators here, C dagger and C. Essentially, the physical meaning is that I have my chain, which is evolving, and then from outside, I add or remove fermions in an incoherent way with rates gamma plus and gamma minus. The important thing here is that this dissipation is diagonal. And this means that if I have the two-point correlation function, G, if I look at the two-point correlation function G of the fermions, essentially what happens is that the eigenvalues of this G are simply related to the eigenvalues lambda tilde of the same G in which I switch off the dissipation. Okay, this is simply the fact that the dissipation is diagonal. And essentially what happens is that the eigenvalues of G are shifted and rescaled by these two factors here, which depend on gamma plus and gamma minus. And then you also get a simple evolution for the density of the fermions, right? So the density of the fermion essentially is given by this formula, where this N0 is the initial density. Okay. Now this system is very simple. It's simple enough that I can compute the dynamics of the generic Rényi entropies. Here, to be specific, I take as an initial state the null state. Okay, so it's the 0, 1, 0, 1, 0, 1 state. Then the von Neumann entropy, let's say, is given by this expression here, where you see what enters is the two-point correlation function restricted to your subsystem of interest. It's not a straightforward calculation, but you can employ this formula. You can suffer a bit with the multidimensional stationary phase approximation, and then what you end up with is this formula here. This formula here resembles a bit the result in the unitary case, so without dissipation. In particular, this term has precisely the same structure. You see, this minimum function describes a linear growth plus a saturation. But there is an extra term which enters here and here. First of all, I should say that this formula holds in a hydrodynamic limit. And for hydrodynamic limit, I mean here the limit of large times, large subsystem size, with the ratio T by L fixed. Moreover, since in the presence of dissipation, everything goes down exponentially, I have also to rescale the dissipation rates, okay, to avoid just seeing an exponential decay. This means that I rescale gamma plus and gamma minus, I send them to 0 with gamma plus times L fixed, okay? This is the regime in which this formula holds. Now, I was saying there are two terms. There is this S alpha mix and this S Y, okay? Now, this term here, you see, is a volume term. And this term is of purely dissipative origin. Essentially, is an entropy that is sensitive to the action of the bath onto the system. This other term here is more like a quantum term, okay? In fact, this is the same that you get in the unitary case. except for the fact that this term here, which would be the entanglement propagated by the quasiparticle, is renormalized by this dissipative term. You see here, this dissipative term appears with the minus, which means that the dissipation actually suppresses the entanglement. And this is what you would expect, right? To be more precise, this these two terms here, S alpha mix and yang are given by this expression here. So they depend only on the momentum occupations, the functions nk, okay? In particular, this mix is given by this average, okay? Is this entropy here, calculated with the density nt, 1, and 1 here is for, to stress that the initial density is 1, okay? And this other term here is the yang entropy calculated from the density with the initial occupation 0, okay? So this term tells you that it's like the odd even sides evolving separately, then you calculate the entropy and then you take the average. This other term here, which enters in this part here, is instead the yang entropy calculated from nt 1/2. Okay, this you see is more of a quantum origin, because essentially what happens is the dynamics smears out this initial inhomogeneity, and then the average density is 1/2. Okay, and then this density depends on time, so it evolves with dissipation. Okay, what we get in this very simple setup. Now, the question that you would like to ask now is the obvious one. So first, you would like to check. Okay, and now let's check it. Here I show some numerics for the von Neumann entropy. Okay, and you see the von Neumann entropy. I mean, this dots here are the exact lattice results, and this line is the formula of the previous slide. And you see some nice agreement. So here I treat only the case in which I have only losses. But the thing that I should stress is that if you look at entropies, essentially you are dominated by this dissipative term. Okay, the entropy is dominated by this purely dissipative term. So what you can do to stress this other part, which is more, let's say, quantum, is to calculate the mutual information. So you construct the mutual information, which is this combination of entropy. And then even at the level of the formula, you see that this purely dissipative term drops out, and essentially the mutual information is sensitive only to this part. And you can check the mutual information. Here is this comparison with the lattice results, and you see that the agreement is quite good, even away from the hydrodynamic limit that in which the formula is supposed to hold. So here is, I think, a bit of some first important message. The message is that despite the fact that the mutual information is not a proper measure of entanglement, because only the negativity is, I mean, the negativity is, but the mutual information is not, still the structure of this formula tells you that it's sensitive to these correlated pairs. So, I mean, in practice, it works as a good measure of entanglement, or at least is sensitive to the entanglement that is generated during the dynamics. Okay, now the important question is, how general is this result? Because we derived it in a very simple setup. Okay, a super simple model. Yes. Okay, I should stress better this point. So my numerical simulations are simulations of the Lymphatic Equation. It's not ab initio, because I would like to have an ab initio simulation, but there are not so many ways to do it, and they are numerically demanding. And here I need to go to this scaling limit, which in practice, I would say, with the numerical methods that we have, is beyond our current numerical capabilities, I would say. If you know a method to do that, please tell me. Okay. Now, we have this result derived in a very simple model. We would like to ask how general it is. And now I want to argue that it's very general, or at least it can be straightforwardly generalized to any quadratic system, bosonic or fermionic. So here I have in mind a generic free-boson model, free-fermion free-boson model that can be brought into this form. This B are Bogoliubov modes, right? So this is you can always diagonalize it and put in this form. And the formula that we want to check, we want to argue is general, is this one. Now, if you want to be general, then the meaning of these two parameters has to be changed a bit, okay? And now in the next slide, I provide you the recipe on how to generalize this the construction that allows you to derive these two terms as alpha yang-yang and as alpha, sorry, here there should be alpha not n mix. The idea is that similar to the unitary case in which the propagating quasiparticles are essentially the Bogoliubov quasiparticles that diagonalize the system, here, what you should focus on are the eigenmodes of the Liouvillean, okay? Because you have a unitary plus dissipative part, so you have a Liouvillean. So essentially, you have to look at the eigenmodes of the Liouvillean, and you can use the fact that you are interested in the weakly dissipative limit, okay? So you can show that for a generic Liouvillean, essentially in the weakly dissipative limit, the equation that you have to solve is this one here. So this beta are the modes, the eigenmodes of the Liouvillean. And you always end up with an equation like that, where gamma is encoding the effect of dissipation, and epsilon is the dispersion of the model without dissipation. This allows you to determine these betas, and once you have these betas, then you can construct the density rho associated to them. Okay. And then the claim is that the yang-yang part of the entropy is the yang-yang entropy calculated from this density here. Okay, so it's given by this formula. Now, the only thing that remains to fix is this S mix. Okay, and this is even easier because essentially this mix, this entropy here is the entropy. You can see it as the entropy of the full system. Okay. And the entropy of the full system, if you use translational invariance, essentially can be easily calculated from the Fourier transform of the fermionic correlation function, okay, which can be at most, let's say, 2 by 2, 3 by 3 matrix, maybe. So this S mix is the entropy calculated from this entropy, from this correlation matrix, okay? Good. So now we have our prediction, okay? And what we can do, we can check it against numerics. So let us consider first the case of bosonic systems. So here I focus on the harmonic chain, which is a system of harmonic oscillators on a ring, which can be mapped to free bosons. And then I perform a quench of the mass of the oscillators, okay? So I start with M0 and then I change the mass to M. And then on top of that, I add a generic dissipation, which is encoded by this matrix here, Cij. And here, to be generic, I allow for rather a general form of dissipation, even a mildly non-local one, okay? Okay, but the dissipation is linear, okay? This is the important point. Otherwise, I'm not able to do anything. Okay, and here I show this quantity, which is this S von Neumann pairs, which is essentially twice the mutual information for a subsystem. And these colored lines are the lattice results, and this dashed line is the prediction that I derived you in the previous slide. And you see that there are some corrections if L subsystem size and time are not large enough, but then eventually everything goes to the. This is an example for a bosonic chain. You can do the same for fermionic ones. So here I look at the Kitaev chain. Okay, and I do a quench in the magnetic field or chemical potential. Again, a generic form of dissipation, and then these curves here are the lattice results. And then you see that as you increase L and you go to longer times, essentially everything falls onto this dashed line, which is the prediction of the formula, the quasiparticle picture. Okay. Okay, so the agreement, I mean, is quite good. Now, for the Ising chain, actually for the Kitaev chain, you can derive this formula that I conjectured in an ab initio way. So this 2-3 slides now are a bit more technical, but I want to give you the flavor of the proof. So the proof works as follows. So the main object is the Majorana correlation function. Okay, for a generic Lindblad equation with dissipation encoded by this matrix K, okay, here I'm restricting to translational invariant dissipation. Then you go to Fourier space, and this Lindblad equation becomes an equation for the correlation matrix in Fourier space, and here this kappa, now this K is a 2 by 2 matrix, let's say, for if you are at one side translational invariant. So and then this K, for K you can take a generic 2 by 2 matrix with these functions A, C, B arbitrary, okay, arbitrary functions of momentum. Okay, now what you have to do, you have to take the weakly dissipative limit. In this weakly dissipative limit, you can show that this gamma can be of this form. So you have a term proportional to identity, one term proportional to sigma y k, and then one term proportional to sigma x. So these sigmas here are just sigma k is a rotated Pauli matrix, nothing so fancy. Now the problem comes when you want to calculate entropy, because you have to invert the Fourier transform to go to real space, and then restrict your correlation matrix to your subsystem, and then you have to plug into the formula for the entropy. So the strategy is to expand this formula, and then what you get is the trace of arbitrary momenta of the matrix gamma. And then if you know the hydrodynamic limit for all these momenta, and you know the analytic dependence on the exponent alpha here, and then you can resum the series and get the result. So this is what you do. It involves some combinatorics, but in the end, it's not impossible. So we did it. So and then if you do it, essentially you arrive at this formula here, which is the formula that I showed you before, where now you determine these functions S yang and S mix, and you get what we conjectured a few slides ago. Okay, so this for Kitaev chain, you can prove this. You can prove everything analytically. Now, what I told you, I told you about only von Neumann entropy, Rényi entropy submutual information, but I didn't tell you anything about the logarithmic negativity, which is something which is much harder to compute. And in fact, so far we managed to do the computation only for the tight binding chain with the gain and loss dissipation. Now, if you do the computation, essentially you get this formula. And this formula has the structure that you expect. So from the kinematic point of view, so the kinematics of these quasiparticles is given by this piece here. See, this is the same as the term you get for the mutual information. So from the quasiparticle interpretation, it has the same structure as the mutual information. The only difference is that here, the negativity content of this quasiparticle, which is given by this function here, is not the same as the mutual information, right? It's given by this horrible expression here. And so far, we don't have a physical interpretation of this expression, but I believe it's possible to get one. Okay. Now, from the qualitative point of view, what happens is that the negativity exhibits the same rise and fall dynamics, so the same qualitative dynamics as the mutual information. It has a quasi-particle picture interpretation because this term here is the same as you have for the mutual information. There is no simple interpretation of this function ek, okay? And in particular, what I want to stress is that this function is not the same function that you get for the Rényi mutual information with the Rényi index 1/2. And this is, I want to stress this because in the absence of dissipation, so for the unitary case, you can show that the negativity becomes the same as the Rényi mutual information with the Rényi index 1/2. So this is a result that has been shown here, and it has been also derived in CFT. So this is again another link with the CFT. In the presence of dissipation, this is not the case. Now, I think I can move on to the second part, discussing dissipative impurities. So now I will consider the case, actually, for the rest of this presentation, I will consider the case in which you have an initial, an initial state, and then you have gain and loss dissipation acting at the center of the system. This is actually a problem, again, that you can treat analytically. So here there is the recipe that you have to follow if you want, let's say, to compute the fermionic correlation function. You have this equation here, which is the unitary part. You have some localized source term. And then there is a standard strategy to solve these problems. In the end, it's free-fermion, it's not so, this part is not so difficult. So you have an ansatz, a factorized ansatz for the 2-point function. in terms of these functions S, and then you get an evolution for these factors S, and then Fourier plus Laplace transform gives you the solution. And then, in fact, you can get almost a fully analytic solution. So essentially, you get these two. I mean, this S as this structure here. So this is a Bessel function, and this K here is an horrible thing because it's the inverse Laplace transform of this object here. So, and it's not. I'm not aware of any simple closed expression for this inverse Laplace transform. But then, I mean, you want something that is to a certain level universal. So what you do, you take hydrodynamic limit. So essentially, you take X and Y large, T large with the ratio fixed. Now, if X divided by 2 T and Y divided by 2 T is fixed, but are different, you can get some result. But the formula looks still quite ugly. So instead, if you send, I mean, X to Y, so you consider this other limit, essentially this function S becomes much simpler. So you get a plane wave plus some kinematic constraint, and then this R is this form here, and this you recognize it because essentially is the reflection amplitude of a delta potential, right? Okay. So actually, is almost that because here you have the absolute value of the velocity of the fermions. If you solve the one-dimensional problem with the delta potential in the continuum, here you have K, simply because the continuum the velocity is K, right? So this is what I show here. The difference is that the strength of the delta is imaginary because the impurity is dissipative. Okay, this is the only difference. And this implies that if you compute the transmission coefficient and you calculate 1 minus tau square minus R square, this is not 0. It gives you some A square, which is the probability of absorption of the fermion at the origin. Okay, this is the only difference as compared with the delta scattering by delta potential. Now, I mean, you can get very compact expressions for the fermionic correlation functions. Here, I give the expression for a generic case in which you have as initial state 2 Fermi Cs on the left and on the right, characterized by 2 Fermi momenta K left and K right. And then you see everything essentially depends on this reflection coefficients. And then you can actually compare with the ab initio simulations. And then you see this red line here is this formula here, and then these points here and the lattice results. I mean, this is a quite simple problem, but it's still nice to see that everything works so nicely. Good. Now, I would like to now compute entanglement, and the entanglement is a quite different beast because, I mean, it's a very complicated function in terms of the fermionic correlation function. So here I consider the case in which the state is a uniform Fermi C, and then I have a localized loss at the center of the chain. And then I focus on these 2 partitions. So here my subsystem A is next to the impurity, and here is centered around the impurity. Now, from the previous slide, we know the fermionic correlation function is given by this formula here, quite simple. So first of all, what should I expect for the entanglement? So this is a dissipative problem. So one could expect also that, I mean, that entanglement is suppressed. But you shouldn't forget that the dissipation source is localized, so it can act as an impurity. And when you have an impurity essentially embedded in a fermionic system, what happens is that these fermions scatter with the impurity. So what happens is that you have a reflected and transmitted wave, and this reflected and transmitted wave in general are entangled with each other. So here, with time, there is a continuous production of these pairs formed by the reflected and transmitted fermion. So there is a continuous production of entanglement, even though the impurity is dissipative. There is another point, and the fact is that essentially, even if you start from a 0 entropy state, like the Fermi C, what happens is that you absorb fermions at the origin. So this profile is affected by this fact. So it changes with time, and it becomes similar to more like to a finite temperature-like profile. This means that there will be, so this genuine entanglement will be intertwined with correlation that arises from the fact that you have essentially a finite temperature state as time goes on. as I anticipated, given the fermionic two-point function, I can compute the Rényi entropies for a generic subsystem X, okay? And if I do that, I get a quite simple expression, which is given here. Now, this simple expression is given in terms of these functions H alpha, which are the same that Paula was showing yesterday, okay? And you see, everything depends on this absorption coefficient. So now this factor Z, so this is a bad notation, sorry. This factor Z encodes just the geometry. So it's 1 for this partition and it's 2 for this other partition. Simply reflects the fact that here you can absorb fermions from both sides of the impurity, okay? Just a trivial thing. But you see, the thing is that the interesting thing is that everything depends on the absorption coefficient. Actually, depends on 1 minus the absorption coefficient. So it depends on the probability of the fermion not to be absorbed at the origin. And then you have this mean function, which describes a linear growth at short times and then a saturation at long times. So this is what happens in this. The thing that I should stress is that this linear plus saturating behavior is present for both these two cases, okay, for both partitions. But here there is something wrong, you see, because if you, because you would like to argue that entanglement is due to this pair of reflected and transmitted fermion that is created at the origin. But you see here, there is the pair is shared between A and the rest. So of course, A is entangled by this pair with the rest. But here, no, because the pair is either at any time is either within A or outside of it. So here there should be no entanglement. But still, this entropy grows with time. And this is a clear manifestation of the fact that the entropy is not a good measure of entanglement, okay? But still, you get a nice, simple formula in terms of this absorption coefficient. So, in fact, you can check the formula. So now these lines here are lattice results for finite L and finite time, and then this red line is the formula of the previous slide. And then you see, of course, as usual, you have to take the limit of large L and long times, and eventually these lines would become in agreement with this red line. Now, very recently, we managed to compute the negativity. Okay, so with my student in Pisa, Fabio Caceffo, we sat down and we did the calculation, and essentially we showed that for this partition, in fact, the negativity is 0. As it should, because there is no entanglement between this subsystem and the rest, because the entangled pairs produced at the origin are never shared between A prime and the rest, okay? For this other case, the negativity grows with time, so it shows the usual behavior, so linear plus saturated behavior. And again, everything depends on the absorption coefficient, okay, on this combination here, but this function E is given by this expression, okay? If you first see it, you think, okay, this doesn't have any simple interpretation, but actually this is not the case. This formula has a very simple interpretation, which I want now to explain. So in fact, let's rewrite this expression here. So this is written here. Now you can cook up a simple two-state system for the two subsystems, okay? So here let's choose this basis S1, S2, where S1 refers to subsystem 1, so subsystem A, and S2 refers to its complement, let's say, so A2. And now this S1, S2 takes 0, 1 values, okay? These are just two states. I mean, there is no interpretation of them. So, and essentially now you can construct this density matrix, which is 1 minus 2A squared projector over 0, 0 plus A squared. And this is a projector on a maximally entangled state for the two subsystems. If you write this is in a matrix form, is this thing here, then you can compute the negativity by doing the partial transpose, okay? And then if you compute the eigenvalues and then the negativity, you get precisely the expression that I showed you before. So essentially this density matrix tells you that if the fermion is not absorbed, then A1 and the complement are in a product state. If the fermion is absorbed, it means that the fermion sees the impurity, and then there is this superposition of reflected and transmitted fermions, which maximally entangle the two subsystems. That's a very simple interpretation, right? And then to conclude, I want to show something that I was doing recently. I mean, another way to deal with open systems is to use stochastic Schrödinger equation. So, for instance, you can imagine of having fermions, which evolve unitarily under certain Hamiltonian age. But then on top of that, you can add measurements, okay? So, for instance, you can focus on measurements of the density. And this gives rise to a stochastic Schrödinger equation, which is written in this form. Okay, from this you can derive the density matrix. Okay. Now, if you take the average of it, so here is some random noise, some noise. These W's are random variables. If you take the average, so you consider the average state, then you get back some Limblad equation. And in this case, this is the Limblad equation that describes dephasing. Okay, because yeah, you are measuring the density essentially. Now, very recently there was this paper. Okay, and what they managed in this paper was to compute the dynamics of the von Neumann entropy. So this is the von Neumann entropy averaged over the different realizations of the noise. So essentially, you fix the noise, you solve this equation, you compute the entropy, and then at the end you take the average. And then the funny thing about this setup is that due to the measurements, there is a continuous production in time of entanglement. Okay, and they provided this formula here, which has an interpretation which is shown here. So essentially, what happens is you have this quasi-particle picture, and then the measurement, what does, at least in this simple cartoon, is that it kills a quasi-particle, and then at the point where it kills it, it creates a new pair. Okay, so this gives you new quasi-particles every time you measure. Okay, but this was a quite simple picture. What we are arguing now is that this picture is actually yes, this picture is actually nice. It has a very simple physical meaning, but it could miss some important correlations. So, for instance, here we compare the mutual information. Okay. So this we look at the mutual information. So these lines here are the exact results that you get by solving the equation, the Limblad equation, the dynamics. And then this dot line here is this collapsed quasi-particle picture that was proposed recently. And you see, I mean, there is a difference. Okay, there is a difference. So this picture is not super accurate. It works extremely well if you look at the von Neumann entropy. But if you go to more refined quantities like the mutual information, it doesn't work as well. Even though it captures some things, for instance, it captures the fact that the mutual information doesn't go to zero at infinite time, which is precisely due to the fact that due to the measurements, you keep entangling the system. It's the measurement process that entangles the system. So this is qualitatively captured, but quantitatively, this formula is not accurate. And I think one possible explanation why this is not the case, even by this plot here. So here we looked at the tripartite information. Okay, so the tripartite information measures the correlation shared between three parts of three subsystems with each other. Now, the key thing is that the key observation is that if you have only production of pairs, like in this collapsed quasi-particle ansatz, this I3 should be exactly zero. Instead, we find that, I mean, if you go to the usual limit of large L and long times, it seems to scale to, it seems that there is a non-trivial scaling function here. So this means that there are correlations between more than two objects that are present in the dynamics, which are not captured by this. Now, and with this, I think I can conclude. So I don't have many points. So, and this is essentially because I think this is there are so many things, interesting things that one can do that, yeah, I cannot come up with with a list. To really conclude, let me thank you for your attention.
Thank you. So we have time for some questions.
It's maybe a very naive question, but anyway, is it possible to say anything about entanglement spreading in higher dimensional systems, like in 2 or 3 dimensions? Is it something that you have ever thought about?
I mean, you can, I think you could do something with the free models, but yeah. And apart from that, yeah, I don't know. Recently there are these approaches. I mean, so of course what I said is based on the presence of some excitation that you can treat as a well-defined particle with a well-defined velocity and so on. But another question which is related is what happens if you destroy integrability, which means that somehow this concept of quasiparticle is not there. And then what has been done recently is to try to cook up some effective pictures for entanglement dynamics. So there is this how is it called, random unitary scenario, right? So this membrane picture that has been put forward by Adam Nahum, and that, if it's true, it's not clear, but it will generalize to higher, because essentially you have a PD, some simple PD to play with.
So I have a question. So I was wondering, for the fermion chain with an impurity.
Yeah.
So if you were to turn on some interactions, I'm thinking about, for example, like the Kane-Fisher problem of the impurity in an electronegative liquid. So using bosonization or similar techniques, could you extend some of your work?
I think, yeah, to a certain extent, I think this problem has been explored with the Lattinger liquid. Also, very recently, there are some papers by the group of, I think it's Corinna Collat. But nobody looked, I think, at entanglement. So this would be but of course, the impurity you can treat with the Lattinger liquid. I think there could be all sorts of things happening, for instance, some transitions as a function of impurity strength. Because here in this case, for instance, what happens is that no matter how strong is I mean, you never have a sharp transition as you increase, let's say, the impurity strength, but this could change, for instance, with interactions. It could be more interesting.
Yeah, do you expect qualitatively that entanglement will spread faster or more slowly with interactions? Maybe faster.
I think it's not easy to give an answer, right?
Okay.
Because I think it can happen. Yeah. So something that I learned in the interacting case is that, let's say you take XXZ, you can have suppression of transport, because when you have an inhomogeneity, it can happen that the quasiparticles are bounce back at the impurity.
That's right, backscattering.
And this, can happen. And then this suppresses entanglement because you have less pairs that are shared. So if a quasiparticle doesn't cross the impurity, then it's not shared between the two parts. But this backscattering is not always there. It depends on the problem. So I think it can work both directions. It can either suppress or enhance spreading. Yeah.
William?
So, I have a question about the relation between the log activity and the 1/2 activity.
Yes.
Because in general, these two quantities don't have any relation.
Yes.
But somehow you were saying that in many contexts, equilibrium, we found that they were equal.
Mm-hmm.
Can you tell us a bit more about the geometry in which contexts they're equal?
Yeah. I mean, this indeed, as you said, if you look at the definitions of negativity and mutual information, you would never dare to say that they become equal, because the definitions are really so different that you don't expect at all that the two becomes the same. There is something that hints at these results, and this is the following. So if you take a pure system, and okay, you pretend it's not pure, and you compute the negativity, then for a pure system, the negativity is exactly the same as the Rényi entropy. But this holds for pure states, while here we are not considering pure states. Even in the unitary dynamics, it's not, because you focus on two intervals, and there is some rest of the system that you have traced over. So the two intervals are not pure. But the key thing, I think, the key observation is that when you do out of equilibrium dynamics, there are very short range correlations. So essentially, I mean, it's as if the two subsystems were in a pure state, in a way. Of course, this statement holds only in a scaling limit. So if you work at finite time and finite subsystem size, you see some order 1 deviations between the two quantities. But then if you go to the scaling limit, the two become.
But for a generic CFT, take intervals that are disjoint.
Yeah.
The running entropy at the next 1/2 and the longevity are pretty complex beasts. Are you saying that?
There is this result that I didn't quote, but it's a result by Shinsei Ryu, and they showed. I don't remember now the setup precisely that they use, but I mean there is some results from CFT. So yeah, from CFT. So in the CFT you can arrive at the same result. Yes. Yeah, maybe it has to do with the fact that the twist field correlator factorizes, I think, because the negativity would be written in terms of 3-point function twist field. Or yeah, at equilibrium it doesn't hold. So there is no statement at equilibrium. Of course, the two quantities are different because you have some long range, not long, but some power laws. So out of equilibrium, all the correlations decay exponentially. So you can play a lot of tricks that you would not be allowed to play at equilibrium.
Relations, did you show a plot comparing the two, or did I?
In the paper that I mentioned, yes, we did it for the harmonic chain, for bosonic system, and for Kitaev. But and there is actually something more, because there are at least two definitions of negativity. The original one in terms of this partial transpose, and then Shinsei Ryu came up with a different one. And there is an extra result, if you want, that the two definitions of negativity become the same. So this prediction holds for both. So both this original negativity and the fermionic negativity become the same, and they are the same as the mutual information with the Renyi index one. Yeah. So, but it's because it's out of equilibrium.
I have a question on the last part where can you put the slide when you're discussing the stochastic?
Yes.
Okay, so you say that the stochastic sharing equation reduced to the linear.
If you take this equation and take the average over the realizations of W, then essentially you see immediately from here the term linear. Sorry, here you have to take you have to construct rho. So you have to take psi, and then you take the average over W. And then this you have to, I mean, everything here, it has to be interpreted in the Ito sense. So you have to go to quadratic. And if you average, the linear term drops because this W have zero mean. And the quadratic part gives essentially the same Limblad equation, the Limblad equation that describes the phasing. Yeah, sorry, here I was a bit too quick. So this picture is taken from this paper. So the idea is that here, this is the time equals 0, okay? Here you have the initial state. And in the usual quasiparticle picture, you produce pairs. Now here you have these measurements. So the claim was that what the measurement do is to kill one of the. So a measurement can act on one of these. Sorry, let's start from here. So here you have these two quasiparticles. Now here you measure. So you kill this quasiparticle, and on top of that you create a new pair. And then this tree keeps branching, and each branching creates new pairs of quasiparticles. And here, this is encoded here. So you see here, this is the entropy, and this is the usual term that you have in the unitary case, which is suppressed as to E minus gamma t, where gamma is the measurement rate. So this pairs that is created at the beginning has a probability that decays exponentially to survive, but at the same time, you have to integrate over all the possible new pairs that you create by measuring. And this is taken into account by this integral here.
You said that this is a phenomenon. It's not the right quantity to consider.
This is not there?
This is a phenomenon.
Yes.
So it's not the right quantity to consider when you have dissipation.
Right. Yes, that's true. I mean, but you can still, it's a quantity. I mean, it's maybe not a genuine measure of entanglement, but it's still a quantity you can consider. No, I concluded, the conclusion is that this formula is too simple. It doesn't account for all the correlations. So for instance, a more realistic formula would be here, the one in which when you touch a quasiparticle, you kill it, but then you create multiplets of entangled. I mean, but might be that this is not enough. Would still be that this is not enough to. And I mean, it's true that this entanglement here is not maybe a good measure, but you know, here actually each realization of the dynamics is pure. So the dynamics here is pure. For each realization of W is pure. So each quantum trajectory, I think it's for each quantum trajectory, maybe it's a good. The not satisfactory bit is that you take the average at the end, which you argue what does it mean physically. So okay, what does it mean to? Well, okay.
Question. So to come back to the question of so that like, the equivalence between the two quantities out of equilibrium, is it only for jump operators that are linear? Or,
are you talking about this part here? No, wait. Here.
Yeah, exactly. So like so if the jump operator was not linear.
No, but there is a thing that maybe I didn't explain clearly. So if you have dissipation, if you have jump operators, this equality doesn't hold. This indeed here there is a. You see.
No, but you were mentioning that out of equilibrium, when the correlations decay quickly, that we can make basically the corresponding.
Yes, but out of equilibrium, you can be out of equilibrium even without jumps, right? You can here in everything I described, there are two. Yeah, maybe I wasn't clear. So there is both unitary dynamics because the initial state is not an eigenstate, and on top of that there is the jump operators. So it's a combined both unitary and non-unitary dynamics. If you kill the non-unitary part, then there should be this equality. Negativity should be the same as mutual information. Here, what I show is that this formula, I get this formula, so I get a result that has a quasi-particle picture interpretation, but this equality doesn't hold anymore.
One last burning question, yes.
Yeah, at the end, by the Théorie,
yeah.
it says that the quasi-particle picture does work very well for mutual information.
For?
Mutual information.
Well, I mean,
it does work for...
well, deviations are smaller for the von Neumann. In this case of measurements, the deviations are smaller. So, I mean, in the paper we looked at the von Neumann entropy, and the data and the curve are very close. So, I mean, it's very hard actually to argue. So, for this reason, we decided to look at quantity where perhaps the difference was magnified, and it looks like the mutual information indeed shows larger deviations from the collapse quasi-particle. It's an open question how to generalize, first to understand whether there is an improved, a correct quasi-particle picture, and then try to construct it.
Okay, so I think we will close the question period. So next we'll have, let's end by thanking our speaker, Vincenzo.